All right, welcome back, everyone. Today, we're diving deep. I mean, really deep. We're going to tackle one of the biggest, most powerful ideas in all of science. And it's all hidden away in the tiniest of spaces. We're talking about the incredible energy locked inside the atom's core. So yeah, let's get into it. This is our explainer on nuclear physics.
I mean, come on, you've seen this everywhere, right? It's on t-shirts, it pops up in movies. It's pretty much the symbol for genius. It is, without a doubt, the most famous equation in all of science.
But let's be honest, what does it actually mean? Like for real? Well, it turns out that this super simple-looking equation is the master key. It's what lets us unlock the deepest secrets of the atomic nucleus, and it's the answer to how these microscopic atoms can hold such an unbelievable amount of energy. Okay, so to get this, we've got to start with the man himself. Einstein. He's working on his theory of special relativity, and in the process, he kind of stumbles upon this mind-blowing connection between mass and energy. And believe me, it was an idea that would literally change the world.
And this is the big idea right here, mass-energy equivalence. What that means is that mass isn't just, stuff, and energy isn't just heat or things moving around. No, they're actually two sides of the very same coin. You can literally turn one into the other. And this single powerful idea, it's the foundation for, well, pretty much everything we're about to talk about.
So to really see this idea in action, we have to zoom in. And I mean way, way in. We're going on a trip deep inside the atomic nucleus to meet the tiny particles that build our entire world and find out exactly where all this crazy energy is hiding. Okay, before we go further, let's do a quick vocab check so we're all on the same page. Inside that nucleus, you've got two main players, positively charged protons and neutrons, which have no charge. Pretty simple. Together, we just call them nucleons. Now, here's the important part. The number of protons, that's the atomic number, is what makes an element what it is. If you've got 6 protons, it's carbon, always. 8 protons, it's always oxygen. And if you add the protons and the neutrons together, that total gives you the mass number. Got it? Good. Now, physicists came up with a really simple shorthand for all this. It's super easy. You just take the chemical symbol, right? So C for carbon, then the atomic number, the proton count, you pop that on the bottom left, and the mass number, the grand total of protons and neutrons, goes on the top left. It's just a neat little way to keep track of everything. So let's look at a real-world example. You've probably heard of carbon-12 and carbon-14, right? Well, they both have 6 protons. That's non-negotiable. That's what makes them carbon. The difference is carbon-14 has a couple of extra neutrons, which makes it heavier. That's exactly what an isotope is. Same element, just a different weight. And fun fact, most of the carbon on our planet, like 99% of it, is the stable carbon-12 kind. All right, so we've got the basics covered. Now, this is where things start to get a little weird. Let's talk about something I call the mass mystery. It's a puzzle that, honestly, feels like it shouldn't be true. So get this. It feels like it breaks the most basic rule of math. If you take a stable atom, pull out all the protons and neutrons, and weigh them one by one, their total weight is actually more than the weight of the nucleus when it's all stuck together. Let that sink in. No, seriously, think about that. It's like you've got all the parts to build a car. You weigh every single part, then you build the car, put it on a scale, and the finished car weighs less than what you started with. How is that possible? Where did the missing mass go? Okay, let's put a number on it. For just one helium nucleus, that's 2 protons and 2 neutrons, the missing mass is this tiny, tiny number. I know, it doesn't look like much, but it's real. It's measurable. It's gone. And physicists have a name for this. They call it the mass defect. And this is the solution to the mystery, the big reveal. That mass didn't just disappear into thin air. It was converted into pure energy. And we call that energy the binding energy. You can think of it like the universe's most powerful superglue, and it's forged from that lost mass to hold the nucleus together. This is E = mc squared, right in front of us. Mass literally becomes the energy that holds matter together. So we have this incredible binding energy glue. But what's the force that's actually using that glue? Well, let's talk about the forces that bind, because we're about to meet the heavyweight champion of the universe, the strongest force we know of. Okay, so picture this. Inside every single nucleus, there is a constant war going on. You've got the repulsive electric force, where all those positive protons are desperately trying to shove each other apart. But fighting back and winning is the strong nuclear force. This thing is an unbelievably powerful attractive force that just pulls everything together. But there's a catch. It only works over ridiculously short distances. And that right there, that explains why neutrons are so important. As you start building bigger and bigger atoms, that pushing apart force from the protons gets really, really strong. So to keep the whole thing from flying apart, you need to add extra neutrons. They bring more of that strong force superglue to the party without adding any more of that electric repulsion. They're basically the essential peacekeepers inside the atom. So the neutrons are the peacekeepers, trying to maintain this very delicate balance of forces. But sometimes that balance just can't hold. If a nucleus gets too big, or it just has the wrong recipe of protons and neutrons, the forces get out of whack. The whole thing becomes unstable, and it has to change. And that's what we call nuclear decay.
And this process of falling apart has a name you've definitely heard before: radioactivity. All it is, really, is an unstable nucleus breaking down on its own to try and get to a more stable, chilled-out state. To do that, it's got to get rid of its extra energy, and it does that by literally shooting out particles or rays. Now, there are three main ways this can happen. First, you've got alpha decay, which is for the really heavy nuclei. They basically just spit out a whole helium nucleus to lose some weight. Then there's beta decay, which is a really neat trick where a neutron actually flips and becomes a proton. And finally, you have gamma decay, which is less about spitting out particles and more about just releasing a big burst of pure energy, like a sigh of relief. And as you can see, they all have very different superpowers when it comes to punching through stuff. Some can be stopped by paper, others need a thick block of lead. Okay, but here is the coolest part of all this, especially with alpha and beta decay. Remember how we said the number of protons defines the element? Well, if one of these decays changes the proton count, you've changed the element. An atom of uranium can literally decay over time and turn into an atom of lead. This is real-life alchemy. The old dream of turning one element into another, it actually happens. It's called transmutation. And this, my friends, is where it all comes full circle. In every single one of these decays, without exception, if you add up the mass of all the little bits that come flying out, their total mass is less than what you started with. And that lost mass, I think you know where this is going. It was converted 100% into the raw kinetic energy of those particles shooting off. It's E equals mc squared all over again. So you see, that famous equation, the one we see on t-shirts and in movies, it's not just some abstract idea for physicists to scribble on a chalkboard. No, it's the actual physical law that governs the very real and frankly unbelievable amount of energy that's locked inside every single atom in the universe. It's why the sun shines, it's why nuclear power works, it's the blueprint for the power of the cosmos. And that really brings us to the end of our journey today. But it leaves you with the final, massive thought to chew on, right? If this is the kind of power, the kind of secret we've found just by peering inside the atom, just imagine what else we could unlock if we keep digging and truly start to understand the universe at its very core.